hydrostatic pressure. We'll use this example to explain the principle of hydrostatic level measurement. To determine the height or level of a liquid, you need to know the specific gravity of the liquid and the pressure the fluid exerts on 1 square inch of the tank bottom. Pressure, then, would be the variable used to calibrate a hydrostatic level sensing system. Remember, the head pressure of the fluid in a vessel is used to determine the height of liquid. For hydrostatic level gauging of open tanks, a differential pressure transmitter is often used. Here, atmospheric pressure is input on both the high and low side of the transmitter. The high-pressure port senses the atmospheric pressure on the fluid in the tank and the hydrostatic head pressure. The difference between the pressures can be converted to level. The low-pressure port senses only atmosphere. Hydrostatic level sensing is also used in dip pipe applications. In the example shown here, gas flows through a pipe that's submerged in the tank's liquid. A differential pressure transmitter measures the back pressure on the tube caused by an increase in the tank level. The high-pressure port here senses the pressure increase caused by the back pressure in the dip pipe, and the low-pressure port is vented to atmosphere. Regardless of the application, the same calibration procedure applies for any differential pressure level measuring system. A low-pressure calibrator is the input measurement standard for this setup. It provides and measures the low-pressure values typical of differential pressure. A low-pressure calibrator contains both a regulator and a pressure transducer in one package. This calibrator displays pressure on a digital display. Pressure is shown in either pounds per square inch or inches of water. A milliammeter measures the transmitter's output. The milliammeter, power supply, and transmitter should be connected in series. Be sure the electrical connections are secure. So that the calibration will simulate the actual operating conditions, the transmitter is mounted in the same position as it is installed in the process. This is especially important for differential pressure calibration because the deflection of the sensing element can be affected by gravity. The transmitter is connected to the low-pressure calibrator. Remember, the source of pressure is connected to the high-pressure port only. The low-pressure port should be vented to atmosphere. Once the equipment is connected, you'll need to determine the instrument's range and the appropriate test points for calibration. To do this, you'll need to know the minimum and maximum pressures the transmitter will be subject to. The lower and upper range values must be adjusted to compensate for the liquid's specific gravity. To find the lower range value measured in inches of water, divide the minimum height of liquid in inches by the liquid's specific gravity. The upper range value is the maximum height of the liquid in inches of water divided by its specific gravity. The span, then, is the difference between these values. The test points should be 10, 30, 50, 70, and 90% of the transmitter's span. Now, a 5-point upscale and downscale check can be performed. When this instrument is properly calibrated, the milliamp output will represent the same percentage of span as the input points. These readings represent the results of the 5-point check for this transmitter. The results of the calibration check show that this transmitter is not operating within specifications. Both a span error and a zero shift are indicated. The zero should be corrected first. With the input pressure at 10%, adjust zero until the output produced is 10% or 5.6 milliamps. Next, correct the span error, applying 90% input and adjusting the span until 18.4 milliamps is produced. Keep checking the zero and span and adjust as needed until they produce values within specifications. Then, do a final 5-point check to verify the calibration and record the values. We've seen that in open tank applications where a differential pressure transmitter is used to measure level, a low-pressure calibrator can be the input standard. In setups like these, the process liquid's specific gravity and operating levels of the tank are used to determine the instrument's range and ultimately the test points used for calibrating. Hydrostatic level gauging is also used for closed tank applications. Like open tank level gauging, Liquid level can be determined by measuring the pressure on the bottom of the tank. But closed tank applications must also compensate for the static pressure in the vapor in the space above the liquid in order to accurately measure the head pressure of the liquid alone. One way to do this is to use a reference leg, which is a pipe connecting the vapor space to the low side of the differential pressure transmitter. The reference leg can be either completely dry or completely filled with liquid. Let's look at how differential pressure is used with a dry reference leg first. In the system, the dry leg should be connected to the low-pressure port of the transmitter. The low-pressure port receives the pressure of the vapor space. The high side also receives vapor pressure in addition to the pressure from the liquid. Vapor pressure, then, is the reference to which the liquid pressure is compared. The value measured by the transmitter then represents only the pressure of the liquid. That's because vapor pressure is applied to both the high and low sides of the transmitter. For calibration, you'll apply pressure to the transmitter's high-pressure port and vent the low-pressure port to atmosphere. Calibrating the differential pressure transmitter used in a closed-tank, dry-leg system follows the procedure for a differential pressure transmitter with no reference leg. To determine the test points, though, you'll need to adjust the transmitter span for the specific gravity of the liquid in the tank. Let's look at an example. These are the minimum and maximum levels and specific gravity for the system. Remember, the low range value is equal to the minimum level in inches, and the upper range value is equal to the maximum level in inches. Now, we've calculated the test points and recorded them on this calibration datasheet. The 5-point check is identical to that for a differential pressure transmitter with no reference leg. After making the checks, compute the transmitter's accuracy, identify any errors present, and make the appropriate adjustments. Now let's take a look at calibrating a transmitter used to measure liquid in a closed tank, wet leg system. Often, it's necessary to use a reference leg filled with liquid for gauging the level in closed tanks that contain volatile fluid. This setup is called wet leg. This type of system prevents hydrostatic head errors that can sometimes result from the condensation of vapors in a dry leg. A typical wet leg is completely filled with a non-volatile liquid that's stable under normal ambient temperature variations. Vapor pressure acts on both the tank contents and the fluid in the pipe, producing an equal reference pressure on both sides of the differential pressure transmitter. The differential then represents only the pressure of the tank level. However, the column of fluid in the reference leg imposes additional hydrostatic pressure on the low-pressure side of the transmitter. This additional pressure must be compensated for to correctly gauge level. To determine the additional pressure that the reference leg will apply, take the height of the wet leg in inches and divide it by the specific gravity of the fluid. The reference leg fill liquid may be different from the tank contents. When calibrating a differential pressure transmitter for a wet leg application, it's good practice to apply the hydrostatic pressure of the liquid in the wet leg to the low side of the transmitter. In this procedure, connect the low-pressure calibrator to both ports of the transmitter. A regulator is used to add the hydrostatic pressure of the wet leg to the low side. Then, zero the output until 4 milliamps of output is produced. In some cases, the zero screw may not provide enough adjustment. In this event, you'll suppress the zero value with the zero suppression adjustment. Once the zero has been adjusted, you can begin a 5-point check to the high side using a second regulator. Remember, the 5 test points you'll use for calibrating the instrument represent the 10, 30, 50, 70, and 90% of span, adjusted for specific gravity. Complete the calibration procedure as you would for any differential pressure transmitter. Make a 5-point check, determine the instrument's accuracy, and identify and correct any errors. Then make verification checks and any further adjustments. Process conditions frequently dictate that a differential pressure transmitter used for hydrostatic level gauging be mounted at a location other than the tank's minimum measurement level. Such an arrangement affects the calibration procedure. For systems where the transmitter is mounted below the minimum measuring level, you must compensate for the additional static pressure by elevating the zero value. If the transmitter is mounted above the minimum measuring level, you'll compensate for the decreased static pressure by suppressing the zero. In this case, the zero is suppressed by a value which is the distance between the minimum measurement level and the transmitter's location, divided by the liquid's specific gravity. This formula is also used to determine the value you'd use to elevate the zero. As we saw with the wet leg calibration, if the application dictates elevating or suppressing the zero, you'll do it after calibrating the transmitter's span. Once you've made a 5-point check based on the total span, you'll identify whether the transmitter needs calibration and correct any errors present. After the transmitter is verified to be in calibration, you'll suppress or elevate the zero by the specified amount. It's good practice to recheck the transmitter calibration once the zero elevation or suppression has been made. Calibrating a differential pressure transmitter that's used in hydrostatic level sensing requires a few special calculations. To determine the appropriate test points, you'll use a span value that's been adjusted for specific gravity. And with some applications, you'll determine the additional hydrostatic pressure that's applied to the transmitter's low side. Sometimes the zero will require elevation or suppression by a calculated value. However, after these specialized values have been figured and applied, the actual calibration procedure remains identical to other differential pressure transmitter calibrations. In the next segment, we're going to see how liquid level can be measured using a displacement level transmitter. But for now, stop the tape to review what you've learned about liquid level measurement using differential pressure. Displacement level transmitters provide continuous measurement of liquid level. We'll use this transmitter to examine the principles of displacement level measurement and calibration. For demonstration purposes, the chamber has been replaced with one that allows us a view of the level. Buoyant force acts on a displacer that's submerged in a liquid. The displacer is reduced in weight by the weight of the amount of fluid it displaces. The movement of the displacer is translated to a torque tube, which converts the movement to a 4 to 20 milliamp instrument signal. The spring action of a torque tube is nonlinear. Nonlinearity, then, is not an error that's adjustable for this instrument. However, the friction inherent in the mechanical movement of the displacer and torque tube can result in other errors like hysteresis. Actual liquid level is the input you'll use for calibrating a displacement level transmitter. For this level instrument, the process conditions are not simulated but are replicated for calibration. The most appropriate liquid for replicating process conditions is a safe liquid with the same specific gravity as the process fluid. And the calibration setup includes a milliammeter as the output standard and a 24-volt DC power supply. The output is connected in a series circuit. The buoyancy of the displacer is directly related to the specific gravity of the liquid. The liquid used as input can vary from calibration to calibration because you're replicating actual process conditions. So you'll need to set the buoyancy value before calibrating the transmitter. This value is determined by the manufacturer. Manufacturers typically provide a correction factor to compensate for manufacturing tolerances of the torque tube and the specific gravity of the displacer. The calibration plate is then set using this value. To determine the setting for the calibration dial, multiply the specific gravity of the liquid by the correction factor. Then set the pointer to the compensated value. Displacement level transmitters are classified as direct or reverse acting. With direct action, an increase in level also increases the output signal, and a decrease in level decreases the output signal. With reverse action, however, an increase in level decreases the output signal, and a decrease in level will increase the output signal. Before calibrating the instrument, set the plug to control the action. Here, the plug is set for reverse action. If this installation were direct acting, you change the position of the plug this way. After the action has been set on the transmitter, you'll need to electronically balance the amplifier to produce the correct input-output relationship. Follow the manufacturer's instructions for this adjustment. Let's take a moment to review the steps we've just seen before we begin calibrating the instrument. To calibrate a displacement level transmitter, you first must determine the buoyancy value for the input liquid's specific gravity. Next, you'll determine the correction factor used to compensate for the manufacturing tolerances of the torque tube and the displacer weight. Set the pointer on the calibration plate to the value you determine. Then, according to the manufacturer's instructions, you'll set the plug for reverse or direct action and balance the amplifier to produce the correct input-output relationship. Now you're ready to begin calibrating the displacement level transmitter. You'll check the calibration at the low, full, and mid-range values. When the chamber is empty, the corresponding output should be 4 milliamps. If the milliammeter displays a value that's greater than or less than 4 milliamps, use the zero adjustment screw to correct the error.